Hello friends, I have a very exciting news for you. In this tutorial series, I'll teach you from scratch how to build your very own classification model using the PyTorch framework. We are not going to use any toy datasets, we'll use our very own dataset, and in this case, we are going to use images of dogs and cats. In the first part of this tutorial series, we'll learn how to read in these images. We'll learn how to utilize the dataset and the data loader PyTorch classes to efficiently structure our data in the format our model wants. Then in the second part of the tutorial series, where everything is going to get exciting, we are going to build our custom model using PyTorch. Then finally, in the final session of the tutorial series, we'll train this model with build and also test this model with data the model has never seen before. We'll cover a ton of stuff along the line, so follow this tutorial series and tell me how you feel about it. I promise you will understand everything, and also I'll teach it in a way that anyone with Python knowledge can understand. If you are excited, click on the subscribe button like crazy and let's get into it. And guys, here comes the fun part. I know most of you are excited to code, and so am I here. But before we jump into coding, the code including whatever library we'll be using here will be on my GitHub repository, where you can clone that repository and install everything and write the code yourself. So I think the only library we'll need here is PyTorch. So continue by importing the necessary libraries we will need. So in this case, we will import PyTorch. We don't even need to import PyTorch, but we will import the dataset and the data loader class from PyTorch. So we say from torch.utils, which means utility.data. We are importing the dataset and data loader classes. Okay, so this is all we need. And for data, we have a lot of data that comes with Torch Vision or PyTorch, but we are not going to use that data because in our real world scenario, you would like to train your machine learning models, your AI models on your custom dataset. So for that, we are going to use a custom dataset. Other than that, if you want to use data from, let's say, Torch Vision, then I think you can import from the dataset class. So you can say from Torch Vision, we are going to import dataset, and you will do this if you want to use the dataset that comes with Torch Vision. So in case you want your training data, you can just say train is equal to dataset dot, then we have many forms of data here. You can see we have fake data, data folder, we have mnist, we have cipher10. So that's it. You can choose mnist and fill up some couple of params here to get it. So the root is where you want to download, but we are not going to do that. So let me quickly clear that off. In our case, we are going to be loading the data from one of my folders I have on my desktop, because I know most of you will be having your custom data. So a folder here contains data of cats, so I have few images of cats and also few images of dogs. So the first thing we have to do is to read in this data into our Python file. All I have to do is to copy this particular path. So I'll copy it, and then I'll say okay, our data path is equal to that particular path, and with the help of OS we can iterate through that path and get all the images. So we have to go ahead and import OS. In that folder we have two subfolders, which are cat and dog. So I will say our subfolders is equal to os.list there, which this will list every other directory in that in our data path. So in case we print this, we'll get the cat and dog folder. So let me run this up, and here we go. So it comes in the list cats and dog, and when you come here into the folder, you can see we have cat and dog. So with OS we have been able to get the subfolders, and now we have to just iterate through these subfolders and get our images. So we can say for our folders, in our subfolders, we are going to get our path, and this will be equal to os.path.join, and we are joining our data path with the subfolder, with our folder, sorry. So we are taking this path and we are joining it with cats, we are joining it with dog. So if I should go ahead and print path, you can see we'll have one path leading to the dog folder and another path leading to the cat folder. So you can see, so this is the first path leading to the cat, the second path is also leading to dog. So we can further iterate to get the complete path to our images. So we can also say for our image list, we call the image list in os.list there of path. Our image here is equal to, then we can use even cv2 to read in this image. So cv2.imRead function to read in our image, and the image, the complete path to our image will be os.path.join, and now we're going to join our previous path and our image list, and this will give us a complete path to an image. So we can go ahead and print this image, and I think we'll print a whole lot of images on our terminal if everything is correct. So you can see these are lists of all the images in the particular directory, so they are in their particular pixel values. Okay, so now that we have our images, we have to create two lists where we will append these images and our labels. So I'll say images is an empty list, and our labels is also an empty list. So what we'll go ahead and do is to append our images and our labels. But talking of our labels, we didn't get our labels yet, and to get our label we can just index the folder in order to get all the labels. So we can say label is equal to subfolder.index, and we want to index our folder. So this will give us 1 for the first folder, sorry, this will give us 0 for the first folder and 1 for the second folder. So if you have many folders or many classes of data that you want to do classification or train a model on, when you use the index on them, you can get their class according to how they are arranged. So in our case, in our folder here we have cats and dogs, so cats will be class 0 and dog will be class 1. Then we'll come here and append all of them. So images.append, and we are coming to append our image. We'll do the same thing, our labels dot append, and here we'll append label. So that's it, guys. We've successfully read in our own data that we are coming to use, and this is the complete code you need per our folder structure. This is the complete code you need to read in your own data. Now let's go on and explore the dataset and the data loader class, how to use it to efficiently leverage this data and manipulate this data in the form how your PyTorch model expects. So for that we have to define a PyTorch class. So we'll call it class, and then we'll call this one data prep, which simply stands from data preparation, and this is going to inherit the PyTorch dataset class. So we'll give it the dataset class, and that's it. Now the next thing we have to do is to define our initialization method. So def, which means define init underscore init and save, and in here you have to pass in your features and your labels, or your features and your target. So we'll just pass in features here, and we'll also pass in labels here. We can specify transform, like we want to transform our image. With PyTorch we are working with tensors, so our image by default now are in numpy array or nd array, because by default that's what OPCV gives you. But in order to work with these same images using PyTorch, you need to convert them to tensors. So you need to apply some transformations to these images. So for that, we can define a custom transformation. So we can say transform, and straight we can do it none, so that it will be optional for you to transform or not. And speaking of transform, then we have to import that from Torch Vision. So from Torch Vision, we are going to import transforms, and we'll use this later after our classes. So as usual, self.our features is equal to features, and self.labels will also equal to labels. We do the same thing for our transform, and that's it. So with this, we've defined all our variables we'll be using. We need our features, we need our labels, and we need our transform. So the transform here just means you want to transform your image, you want to resize this image, you want to normalize this image, you want to convert this image to grayscale. Those are the transformations you can apply to this image. Then we have to define our get item. So use df and initialize underscore get item. And what this helps you to do is to get a particular image at a particular index. So let's say I want to get the first image, I can, with this particular method, it will help me to get a first image with its corresponding label. So it's very important, and this is where PyTorch rocks, guys. Image is equal to self.features at the index of item, and we do the same thing for our labels. Then we'll have to check if the user wants to apply transformation. Okay, so if you want to apply transformation, you have to check, because straight off we are setting transformation to none. So in case you want to apply transformation, then we have to check. So if self.transforms, then we'll go ahead and apply that transformation. So call our image, and now our image becomes self.transform, and we pass in our image. That's it. So we are returning our image and our labels in case there is no transformation. But if there is transformation, for the labels they are 1, 0 and so on, so we don't need to apply transformation on our labels or our targets. But for our image, we can transform them, resize them, reshape them, normalize them. So at the end, all we have to return is to return our image. So we want to return the image and label. If transformation is applied, it will apply automatically. If not, it will return them like that. Then the last method we have to define here is the length method. So define underscore length, and this just helps you to get the total length of your data set. And all you have to do here is to return the length of your self.labels. So your self.labels helps you to get the total number of data you are using. So now with this we are done. So we are done with the data set. Now let's move on to the data loader. But before that, we are specifying transform, so we have to apply transform. So for that, I can say data underscore trans, which stands for data transformation, is equal to transforms.compose. So with this transform.compose, it helps you to apply numerous transformations to your data, but in this case we just resize the data and also convert it to torch.tensor. So the first transformation we apply is to convert our data from numpy array to torch tensor, because that's what is much compatible with PyTorch. So what we will do here is call transforms.tensor, and that's it. So very simple. If you want to apply the next one, we can still call transforms.resize, and you specify your own size. So for these images, I will just resize them to 200 by 200, and that's it. So you can see with the transform, we have many transformations you can apply. You can see transform dot, and you can see to tensor, random rotation, normalize, random horizontal flip. So there are many transformations here you can apply to your data, but in our case we are applying only 2. and this is for our transformation pipeline. So now let's instantiate our dataset class. So I'll say dataset is equal to our data prep, and in here now all you have to pass is your features, which in our case is our images. So you can see from the starting we read our images and we've saved all of them in the list called images, and our labels in the list called labels. So we just have to feed in our data pipeline with the labels as well, and then the transformation. So for the transformation we call it what, data trans. So these are the transformation we apply, and with this we can get our data in the shape that we want. So if we should print data set, this should give us probably a PyTorch object. So you can see we have the dataset object created, but in case you want to get some of the data, we can index here to 0. So you can see we had the first batch of data here. So this one image, all these are for one image, and this is its corresponding class. But where this dataset shines is when you use the data loader for it. So the data loader just helps you to get these images in batch, and this batch you specified yourself. So that's what we are going to do next. So for data loader, we can say our data underscore loader is equal to data loader, and what it takes is your already prepared dataset. The dataset that you went ahead and prepared, you just have to pass it here. So we give it the dataset, and here you can also specify the batch size. So the batch size, we can put it to 4, you can put it to 5, 10, any number you want, but you must just make sure that is compatible with your model you are designing, and that's the batch of data you want. So let's put it to 4. So what this means is that at any time if I call this data loader, it will send me 4 images, and without applying shuffle, that means the images will come by default how they are arranged. But when you are training your machine learning model, your AI models, you need to apply shuffle so that any image at all can come from anywhere. It doesn't arrange the images in a particular pattern. So for that, say shuffle is equal to true. With this one, your data will be shuffled. So an image of a cat can come first, an image of a dog can come. It will just mix them all up, and that is the best practice you need to follow. So for our data loader, when we print it, we'll get a data loader object too as well. You can see we have a PyTorch data loader object in this particular memory location. How do we get our data then? This is pretty simple. So let's call this one data sample. We want to get a data sample, that's the first batch, is equal to, then we use the next ether, and then we pass in the data loader here. So with this one, it will return some batches of data for you. So if we should print our data sample, we expect this to return 4 images with 4 labels because our batch size is 4. And here is it. So you can see we have 4 labels here. 1 1, that means dog. All these images are for dogs. So, and these pixel values or these matrices are for 4 images. So you can see we have 4 different arrays here. So that's it. That's simple how you can use it. Let's run it again, and you can see now we have images for all cats, and because we are applying shuffle, you can see everything is just shuffling up. So when you run it again, you are not going to get the same data every time you run it. We have dog, we have cats, we have another cat, and so it's shuffling up, and this is the beauty of it. So with the data set and the data loader class, you can organize your data and send this data into your model batch by batch. So you can even index it that you want only the first image, and this will come with the first image and its corresponding label. So this is how simple it is. So this for data set and data loader. With this, we'll continue next time. In the next tutorial, we'll see how we can build our model in PyTorch. So how to build a PyTorch model. So in our case, since we are doing cats and dog, then we are learning how to build a classification model. So guys, if you love these videos, kindly give me a thumbs up, subscribe to the channel, share this video with some of your friends that might need this, so that we grow a large learning community together. Thanks for watching. I appreciate your time and your effort, and I'll see you in the next tutorial. Hello guys, and welcome to part 2 of our PyTorch tutorial series. In this part, we are going to learn how to build our custom model using PyTorch framework. If you are excited about this part, subscribe to the channel and don't forget to share with 1 or 2 of your friends who might benefit from this. Enough with my self-promotion stuff, let's roll and get the work done. Welcome to the part 2 of this tutorial series where we are building our custom image classification model using PyTorch. In the previous part, which is the part 1 in this case, we learned how to load in our images from folder. So these images include pictures of cats and dogs. And then we use the dataset and the data loader class from PyTorch to structure this image in a particular format our model demands. So in this part, we are going to learn how to build the model. Then in the final part, we will learn how to train this model and test this model on a new data set. If you enjoyed the previous part, kindly give me a like, subscribe to the channel, and also share this tutorial series with some of your friends to benefit from it as well. So we'll start off by importing the neural networks model from PyTorch. So we'll say from torch, we want to import NN as NN. So this is the neural network model in PyTorch. And to build a PyTorch model is pretty simple. So we'll begin with defining our class here. And now to name our model, we just have to call this cat dog model. You can call this anything you want, but just that you have to make sure it's descriptive of whatever you are doing. And in here, we have to use the base model provided by PyTorch for building neural networks, and this is nn.module. So this is a PyTorch base class for creating neural networks. And the next thing we have to go ahead and do now is to define our initialization method. So we do super init, and in here we have to pass in our cat dog model here. So it will inherit this from the parent class, and we shouldn't forget to add self here. Okay, so since we are going to do classification, the best option for us now is to build a convolutional neural network, CNN. So we use convolutional neural network because it's very good for classification tasks. It will help us extract important features from our images. So we'll start off by defining our various convolutional layers. So the first layer, we'll call it self.conv1. You can name it anything, but don't forget the self is equal to nn.conv2d. So we are creating a convolutional layer, and this should take in the input channels of our image. So our image is RGB images, so they have 3 color channels. So in this case, our input channel will be 3, so we just call it input channel is equal to 3 in this case. And the next thing is our output channel. What is the dimension of the output features we need? And in this case, we'll just pass out 64 output features. Then we have to specify our kernel size. So we'll specify this kernel size to be 2 by 2. And the next thing is our stride. So we can keep the stride to as 2. The last one is padding. So for padding, we'll leave padding to 0. This will be output channels. Let me correct that. So the next layer we'll go ahead and also build now is the pooling layer. So self.maxpool is equal to nn.maxpooling layer. So the max pooling layer reduces the features from the convolutional layer. So if the output shape from the convolutional layer is 64, the max pool layer will give you half of that. So we still need to specify kernel size, and in this case we'll go with 2. We will also specify our stride to be 2, and the last one is padding, which we'll keep. So now we'll introduce an activation layer in order to introduce some non-linearity inside our model. So we'll say self.activation, and this is equal to nn.relu. So we are using the ReLU activation function. So this applies a transformation whereby it converts all the negative values to 0, and then it maintains the positive values as they are. So it's just a function that runs element wise in our matrix and then converts all these negative values, -1, negative numbers in this matrix to 0, and then keeps the positive or retains the positive numbers. We can add so many convolutional layers, or we can add many max pooling layers as well, but in our case we want to keep this model so simple, so we'll end this by adding a linear layer. So this linear layer is like our output layer, so we'll add that layer, this self.linear, and this will be equal to nn.linear layer. And in here the input features, they should be 64, and we'll multiply this by 50. Then we'll specify our output features here to be 2. So we are specifying 2 because the output we'll be getting from our model will be 2. It will be either cat or dog. So if you are doing classification where it involves 3 or more outputs, you have to know your output layer should be the number of output predictions you want. So in our case it's only cat and dog, so it's 2. Okay, so after defining our model, now we need to define another method, which is the forward method, in which our data will pass through these layers we've defined. So we'll call this one forward, and here we pass in self and we pass in our data. So we can call our data, in this case let's just call it data. Let's go ahead and pass this data into the different layers we've defined. So we'll first pass it into the convolutional layer. We'll call it out is equal to self.conv1, and in here we pass in our data. Our same out is equal to self.activation, and we pass in our data. So after the convolutional layer, we are bringing in the activation layer to introduce some non-linearity inside our model. And then after the activation layer, we'll introduce our max pooling layer, which is also equal to self.maxpool, and we just pass in our data. After max pool, you have to also introduce the activation layer in order to further introduce non-linearity in your model. Then finally, before we send this data into our linear layer, which is an output layer, we have to bring in a flatten layer. So we can come here and define our flatten layer, which will convert all these multi-dimensional array or matrices into one dimension. So that's what the flatten layer do. So we just say self.flatten, and this will be equal to nn.flatten. Call it here self.flatten, and in here we pass in our data. So this will convert it to one dimensional vector for us. Then finally we'll send this data into our linear layer, and this layer is responsible for our prediction. Then what we'll do here is to return our output, and that's it. And with this, we have just gone ahead and defined our custom PyTorch model. So we can go ahead now and instantiate this model. So we call it model is equal to our cat and dog model. So now we can print how the model looks like, and we say our model.eval. And if we run this, we'll see how everything works up. So you can see the different layers we've defined. We have convolutional layer, we have a max pooling layer, we have a activation layer, another linear layer, and our flatten layer is also here. So guys, this is how easy it is to define your custom model. With this, we are keeping it simple. We can stack many convolutional layers, we can stack many max pooling layers, and we can stack many linear layers. But we are just keeping it simple. Once you know how to do this, you can stack this yourself. Stacking them just means using 2 or more convolutional layers in this same model. But we are keeping it simple once again. So this is all for defining our own model, and this is the end of part 2 in this particular series. In the final part, we will now learn how to train this model and run some predictions to see how best our model is working. We'll also check out the accuracy and evaluate this model and see how good it is. If it's not good, then we'll go one step ahead to stack many layers and see how our model will improve. Or we can also go ahead and apply more transformations to see how our model behaves, guys. So if you like this tutorial series so far, give me a thumbs up, share it with your friends, and as usual, I'll see you in the final part. Thanks for watching. Hello guys, and welcome to our final episode on building our custom classification model using the PyTorch framework. So this is the third part of this tutorial series, and this tends to be the final part of this particular tutorial series. In the previous two tutorial series, I teach you how to load your images. So we use our own custom images, that's cats and dog, and then we used our dataset and the data loader PyTorch classes to transform these images in a particular format our model requires. And in the second part, we built our custom classification model. So we did that by using the nn.module class from PyTorch. So today we are going to train this model and also test this model with our custom data. So we are going to be testing this model with images that the model has not seen before. So before we start off by importing other libraries we will need, in the previous tutorial we had some small mistake here we need to correct. We are passing in data here, so everything here should be data, so we just have to change all the out here to be data. And that's all the modification we'll do. So now let's go ahead and import our optimizer. So we say from Torch we are importing optim, and that's it. So that's it, we have imported our optimizer, our model optimizer in this case. So we'll come down here and define some couple of things. So we'll start off by defining our learning rate, and straight off I'm going to set this to 0.001. The next thing we'll go ahead and do here is also define our epochs. So the number of times our model is going to train, and we'll set this to 100 epochs. We can increase later on. After this, we have to define both our optimizer and our loss function. So for optimizer, we'll be using the SDG, stochastic gradient descent optimizer. We use the optim with imported .sdg. So in here you can see we have various type of optimizers you can use, but in our case we are going to use SDG. You can use Adam and so on. So in your optimizer, what you have to go ahead and do is to send in your model parameters. So we do that by saying our model.parameters. So you can see before we're able to use model.parameters, in our previous tutorial we have the instance of our model created here. So we are using model parameters, and the next thing you feed in is your learning rate, and that's it. So let's go ahead and now define our loss function. With that, we can call this criterion, and this is equal to, we'll use the cross entropy loss. So we go by nn.cross entropy loss. There are different loss functions you can use, and that's it. So we'll go ahead now and define our training loop. For that, we have to loop through the number of epochs. So we can say for I in range of our epochs, then we'll also iterate through our data loader class in order to get our images and their corresponding labels or targets. So we'll say for our image and our targets in our data loader, but before we feed these images we have to write our optimizer.0 grad, and then we take our output here, which is equal to our model, and in here we send in our image. So this is our model. We take our image each time and try to train it. After sending in this image, we have to calculate the loss each time we run through this loop. So you can say our loss here is equal to criterion, and in here all you have to do is to feed in your output and also your target. So it will calculate how far you are from your target and know how to play with the weights and your biases in order to get the model working accurately. So that's how we can get our loss from the model. From that, we do our loss.backward, write our optimizer.step, and that's it. So with this, we are done with our training loop. But what we'll go ahead and do is to visualize our loss, because as we are training, your loss will decrease over time. So we have to visualize this loss. So we can print this, and using some f string, we can say our epochs, and in here we can say that's I plus 1. So you can see we are using I here to loop. So each time we loop through, we add 1 to our I, so that will be equal to the total number of epochs we are currently running. So you can write that one out of the total epoch, which is epoch. That's it. Then the next thing we also care about is our loss. As we are training, is our loss going down? So we can also get access to the loss here. So call it loss. You can bring some bars here for better visualization, and we'll say our loss here, and this will be loss.item. Okay, so this is it. So immediately I run this will start the whole training process, and we can see. So let me run this and let's see. This is our architecture we are running. So you can see this starts our training process, 1 out of this, and you can see as it's training, the loss is going down. So once your loss is going down, this signifies that your model is training and is training well. But we have to also show the accuracy, and you can see this is very slow because for now we are training on CPU, so it will take a whole long time to train this model for us. We don't want that because this particular computer I'm using has GPU, so let's utilize the GPU capability and also implement the accuracy so that we can see how our accuracy increase over time as our loss decreases. So I'll just break this, and then I'll come to the top here and say our device here is equal to CUDA. So CUDA here means GPU. So we are going to use our GPU if torch.cuda is available, else we will use our CPU. So if your computer is having a GPU, then you can do this. If not, then you have to train using your CPU, which is time consuming. So since we have our device here, if we print this, it will either give us CUDA or CPU. So when you get CUDA, that means you have your GPU set up and everything is working. Now getting it, we have to come down here and move everything to the GPU. So over here we can move our model to the GPU, so .2, then we add device here. Then the next thing we'll do is to move also our images and our target labels, because our images here are tensors which we are going to train. So we have to move the images and their corresponding labels to the GPU. So we can simply write image is also equal to the same image dot device. We do the same thing for our labels as well, and that's it. So with this small adjustment, we can be able to train this model now utilizing our GPU, and I'll run this so that we see the increase in speed using the GPU. So you can now see how fast this model is training as compared to the previous one without us utilizing the GPU. So that's it. Now let's implement the accuracy, and then we'll train and save this model and reuse it, which is our final step. So I'll still cancel this up, and then to calculate our accuracy, we can define that our total correct, so total number of images the model is able to get them as correct values. We can start it with 0, and then we can also get the total sample. So total underscore sample, that is the total number of images, and we can equate it to 0 as well. Now we'll come inside the loop, and then we can get the predicted output here, right? After feeding the images into our model, we can get that from the output. So we'll take our predicted output, so we call it predicted, and this will be equal to touch.max. Okay, so now after getting this, we can go ahead and each time we'll increase our total number of samples. So we can say our total samples is plus equals target, then we do dot size. So we use the size method and then we get the first one, which represent the total number of samples in our images. So each time through the loop we add it up. So for every iteration in our loop we get 4 images, so it will be adding up. We get 4, that's the total number of samples. Through the second iteration it will add up and so on. So that's how we'll get the total number of samples. Now we should get the total number of outputs that the model guesses correctly. So for that we can call our total correct, and this is also plus or equal to, into parentheses, everywhere that our predicted is equal equals our target. That means that particular one is correct. So anywhere our predicted value from the model is equal to our target value, that means the model have been able to predict that correctly. And then we can go ahead and sum all of them up. So we use the sum method, and then after summing them we get the item, so dot item as well. So this is how we can get the total correct and our total samples. Okay, right after getting this we can go ahead and now calculate our accuracy. So we can come down here and get our accuracy, and we'll call this one accuracy, and our accuracy will be equal to our total correct divided by the total samples, and that's it. So with this we can easily get our accuracy, and I'll go ahead now and also display our accuracy as we train along. I just love putting double slash here so that it looks just nice. So with this we are done printing out the important things we want to see whilst we are training our model. So what we also want to do is to save this model as it trains. So as we are training the model, we have to save the model. So for that we'll come down here and go ahead and save the model, so that you don't get to train the model each time you want to use it. So you can save the model and then you can reuse it anytime you want it. So we can save it by just writing touch.save, and in here you have to provide so model.stateDict, and that's it. So with this, the next thing you have to provide here is the name you want to save this model with. So we will call this one cat dog model because we are training cat and dog images. So we can just call this cat dog. I guess I've done that before. So model.pt, so that's the name we'll give to the model. We give it cat dog model.pt. You can give it any name you want, but make sure you have the .pt extension at the end of it. So this will go ahead and save our model, and after saving this model we can go ahead and print model saved. So now I'll go ahead and run this, and this will go ahead and train and save our model. So after training and saving this model, we'll go ahead and test this model on unseen data. So we just go ahead and load the model and then give it an unseen data. We'll read a new image using OPCV, and then we send this image into our model to predict whether it's an image of a cat or a dog. So that's what we'll do next. So let me quickly go ahead and run this so that it trains our model. So you can see the training process is much faster. We are using only 100 epochs, and we are 23 out of 100 now, and you can see our accuracy is increasing over time. Alright guys, so we went ahead and trained this model, and the model is saved. So you can see model saved successfully. So we can bring this down here since our model is saved, and you can see the name of the model being saved here. Next, you have to read in this saved model so that we can use it. We don't have to train this model again. So for that, all we have to do is to comment the training loop, since we are doing it in the same file and the model being saved here. We can comment this whole code, and then we'll go ahead and load in this model and use it. So we can call this loaded model, and this is equal to an instance of our cat and dog model. Then we'll go ahead now and load the actual model. So loaded model dot load state date, and just as we've saved it, we can use the same name for it. So in order to run faster inference on the images you want to test it with, you have to also utilize the GPU so that you get faster speed. So we will do our loaded model is the same as our loaded model dot to, then we put it on the device or our GPU in this case. So you can even go ahead and evaluate this model by printing model.eval, but since we've saved this model and we've done that ahead here, we are not going to do the same thing. All we care now is to load in the image and then send this image into our model for prediction. So for that, what I'll do is define an image path, and this will be equal to, I have some other images on my desktop, so I have to just bring in that path here, and then we send that image into the model for prediction. We can do our image here is equal to cv2.imread, and we are going to read whatever is in the image. So now let's go onto my desktop. I have some images of dogs here which are not part of our training data, so I can just copy this particular path. So these are reserved images. I just used 200 samples of cats and dogs to train that, but actually I have a lot of images here I didn't utilize for the training process since it's a short tutorial series. So I'll copy this path and then I'll place it right here, and then we'll do / some name of one of the images. So we have, let's test it on this one, this particular image. So this one is dog4912.jpg. so I'll just type that there. Okay, so I'm reading that particular image, and then after reading this image, we need to perform the same transformation we've performed when we were training our image. So that's one thing about machine learning and artificial intelligence in general. The same way you've shaped and transformed your image before using it to train the model, when you're about to test this model with another data, you need to transform the data into that same format. We define a transformation pipeline here, data transformation, and what we are doing is to convert the image into a PyTorch tensor and also resize it to this particular size. So since we have this transformation here, we just have to call it and pass in our image. So we'll just do that, and then we'll transform our image. So I can put this into input underscore image, and this will be equal to our data trans, and in here we just pass in our image, and that's it. So right from here our image will be transformed, and now after transformation, what we'll do is to send this into the model. So we'll start off here, we say with torch.noGrad. Our output here will be equal to our loaded model, and in here we just give it our input image. So that's it. We just give it the image, and this will return some output for you. So in order to get this particular output, we need to use our torch.max, the same thing we did right here, in order to get the particular class the output belongs. So I'll just copy this right here and paste it out. Okay, so we'll call this one predicted label. So this will be the label in which the predicted class belongs. Okay, so after getting that, we can define a class. So a class label maps kind of thing, so that we map it to dog or cat when anything is being detected, or based on the output we match it whether it's a dog which is detected or it's a cat. So we can do a class underscore label underscore map, and this will be equal to a dictionary where we'll map 0 to cat and also map 1 to dog. So that's it. So we are just creating a label map that we can map to whatever we've detected. So if we detect cat, then we map it to cat. We detected dog, we map it to dog. So the output here will be either 1 or 0, and we know 0 belongs to cat and 1 belongs to dog. Sorry, all of this shouldn't be indented. Okay, so now our predicted label will be equal to our class label map, and in this we can say our predicted label, that is our predicted label. Okay, so whatever item we are getting from this our predicted label, if it's 0, we'll map it to cat. If it's 1, we'll map it to dog. So we can go ahead now and print it. So we can print, and in here we'll put our predicted label. Since they are all string, we will not use f string. So that's it. Okay, so predicted label, no, this is our predicted class, right? So we have to change the same thing here, our predicted class, and that's it. So now, so with this we can be able to test this out. So let's run this and see. Okay, runtime PyTorch float tensor weight. So okay, I know what is happening right here. So before we train our model, you can see we have these images in 4 batches. So now we are only sending one image to the model, which the model, due to the shape, the model can't really give us any output. So for that we have to transform this image. We can use the onSqueeze method in PyTorch to trick the model in such a way that it will understand that we are passing 4 images, but in actual sense we are passing 1. So to do that, we'll come down here. So what we'll do here is to do dot onSqueeze, and we are altering the dimensions, and then we'll put it to the device. So dot to device, so that we tend to run it on the GPU as well. So that's it. Let's test it out right now and see. Boom, and it said our predicted label is a cat, which is a lie, because let's see, what we are feeding in here is an image of a dog. So why is it saying it's a cat? Alright guys, so here we should be taking our output dot data, and we are just taking the output. So that's why we are getting wrong predictions. So let's try this once again, and boom guys, you can see our model is rightly predicting that this is a dog. So I think that is the mistake I've done, and I'll even move back once to test it with that same image to check how well it will predict. So let's see whether it gets it this time as dog, and boom, you can see here we go, this model is working greatly. So I'm using only 400 images, that's 200 for dog and 200 for cats, to train this model. So you can see our model can classify dogs very well. You can change it to 14 here, which is another image. So is this image right here? You can see this image right here. Let's also run it and see whether or not it will predict it's a dog. So it gets it right, it's a dog. So guys, this is it. This is how easy it is to build your very own classification model. So we started by loading our images, transforming these images, building the model, training the model, and testing the model. So this is like a whole hip hop journey we've embarked on, and these are the processes you have to follow to build your very own classification model using the PyTorch framework. So as you can see, it's straightforward. Thanks for embarking on this journey with me. Let me know your concerns, have your comments in the comment section guys, and also like and share this video. Let me have your feedback, general feedback about this tutorial series, and let me know where I can improve more. If you like this video, as usual, just share, subscribe, and I'll see you in the next tutorial.